pulling data directly from the model, so the model wouldn't even know that it was, something was pulled from there, right? So here, right, that's a push model. Why? Because we see that observers are notified here, right? So their update method, we call the update method, and we provide both arguments, but here we do not use the obj argument. We just use the arg, right, which is a reference to the new data, right? So that's the push model. All right. Here is an example. Where do we have it? Yeah, here's an example of the pull model. Right? We have an update method similarly, but we ignore arg and we use obj, the observable, right? The model. So this is our observer, and it uses the model obj to pull data from the model. Okay? So we use the observable. In the pull model, we use the object, the arg, the data, and the push model. All right, that's translated to this example. Right, we have an observable and an argument here as the parameters to the update method, and we're using O. Right, O is an observable. So what kind of model is this? Pull, push.
Oh.
Yes, please. All right.
I feel like, is this push?
Okay, so let's see. In the push model, the model pushes their updates to their observable, to the observer, right? So it would call update and provide the new data in this argument. Right? That's not happening here, right? Because their observer doesn't use this arg. It uses O. O is the observable. O is the model. So see how their update method of the observer uses O's size method, right? This method. Basically check what is your current size. So it pulls data from the model, right? It says, well, model, give me your current size, please. Okay, so the model doesn't even know that it's been queried for new data. So this is the pull model. All right, so now in the glide, if we have this code, all right, so we make a new sign-up sheet, and then we add a student to this sign-up sheet, which is our model. So what happens? Nothing happens. Right, why?
Because you're not supposed to see anything. This is on the controller side, and this is happening. The update is happening between the model and the view, right?
Right, but when update happens,
Yeah. So
there is a println that says sign-up count. So every time we add a student, we are supposed to see the new count, and it's not happening here. All right, so notify observers. All right, we've seen this implementation earlier. It's just a for each loop over all students, and we call update on not students over all observables, right, that have been added, and it just calls update for each of their not observables, observers, and it's notify observers just calls update on all the observers that have been added. And that's not happening here. Why? Because in order for observers to be called by the notify observers, those observers need to be added to their model first. The model needs to know which observers it needs to notify. Okay? So remember, there is an add something like add observer method that we have to send the observer into, so that the model keeps track of those whom it needs to notify. If the model doesn't have any observers listed that it needs to notify, then it's not going to notify anyone. Right? So it's crucial that an observer is actually added to the internal list of observers that the model, our observable, maintains, and then when we add a student, all right, then it's going to work. Okay, so and this is the controller, of course, right? But it is important that we have properly connected all necessary observers with their observable. All right, so here is another example, right? Slightly more involved. So we have a sale total frame, and we have property listener that is basically an interface that we want to represent the idea of an event that needs to be fired when some property changes, right? So what is the observable? What is the observable? What is the observer here? Sale is our observable. Sale is the model sale. We'll have the properties, and then sale will maintain a list of observers. Right, so see how we have add property listener, right? And then when this event happens, we will go over all property listeners here, right, in our published property event, and we will call this off property event for each of the listeners, right? Listener is just another name for an observer, right? So that's that, right? So this is we'll call notify, and notify will update all the observers. All right, so this observer pattern is known as model view controller or model view, and there are different variations of this pattern, right? So there's really more than one or two. One of the very common things that can be done is view can actually be combined with a controller. Okay, so then we have just a model view. Right? It is crucial that model is very well separated from the rest of the objects. But view and controller can sometimes be very difficult to cleanly separate. Right? Because view is related to how we present information, how we present the data that model exposes to the user, and controller is also interacting with the user. Right? So yeah, in most cases you can kind of separate the controller, but whether it makes sense or not, it depends on the problem. Right? So in your homework 7, we definitely insist that you separate the model. And if you don't want to cleanly separate the controller from the view, if you only have one view, it's okay to have like a common view controller. Right? As long as the model is separate, it's going to be fine. All right, so this we already talked about why observer and observable are deprecated in Java 9. It's not because there's anything wrong with the model, with the design pattern, but because it wasn't implemented particularly well, and so it's not serializable, it's not thread safe, there's a number of issues, and unfortunately in Java they didn't come up with just a better replacement for this observable interfaces. They didn't really offer a good solution. They offered, well, I mean, within the standard Java, right? So they say, well, you can probably use Java Beans, which is a sort of a more advanced concept that belongs to the Java Enterprise Edition. Right? And there's a number of similar alternative solutions, but none of them would fit within the context of our Java knowledge, and therefore we're just sticking to observable, despite the fact that it's deprecated. Again, nothing that we care about, right? We are not doing multi-thread programs, so we don't care whether it's thread safe or not, right? We're not running it on multiple threads. All right, so that's that, and functional implementation. So let's keep it as the same, just using the more recent kind of functional approach to writing Java code, so we can sort of skip that and go directly to our next pattern. It is called facade. Right, so this little thing under C makes it sound C, not K. Right, so it's not facade, it is facade. Well, believe it or not, right? So if you remove this thing, it should be read as facade, right? But it's a French word, so it's cécile, and that's why it's facade. All right, so what is this facade design pattern? Basically, it says that if we have a complicated library with lots of features, this library is complicated and it's hard for a user to utilize this library. Maybe the user doesn't really need all the features of the library. So we want to present a simpler view of the library to the user, right? So there's several examples. We want to perform secure file copying, and there's a very powerful, complex general-purpose security library that can copy files, among other things, but that can do a ton of other things. And we don't want to confuse our client by telling them, well, just use that general-purpose security library, because it would be very hard for them to start using that library correctly because it's so complicated. So we can give them a shell that will internally translate all calls to this general-purpose security library, but that would expose to the client only a limited number of methods that are sufficient for their user to solve their problem, like to copy files from one machine to another. All right, so this is the basic idea of a facade pattern, right? So facade, right? It's something that is up front, right? It's sort of the front end. So here is our complicated general-purpose library, right? This one. Right? Many components and many ways to interact among them. So our client is built, right? So this is our client at the top here. Right? If it uses the library directly, it needs to know everything about the library and all the pieces of it. What we want to do is have a shell, let's call it secure copy, that presents to the user a simplified view of this library. Of course, it's going to have it's only going to expose not all, but only part of the functionality of their actual library. But it is desirable in this case because the interaction of the client with our facade becomes much simpler, right? So basically, it's just a single entry point to this entire library. So for the client, things become very easy if they use our facade. Right, so facade reduces their interactions between the client and the complex library. So basically the goal of the facade is to present a simplified view of some library. All right, so there is an additional advantage that if this underlying library changes, then we only need to update our facade, and the client doesn't need to be modified. All right, so in a sense, this is similar to adapter, which is one of the patterns that we will review shortly. Right, in that sense that it kind of allows to match the requirements of the client with the capabilities of the library.
I think this is pretty similar to the graph wrapper before.
Yeah, exactly. All right, so. All right, so as I mentioned, it's lake adapter. It's also similar to proxy, which is yet another pattern which we will talk about. Right, hiding the complexity of the underlying system from the client. Right, with the graph wrapper, right, whether it's a facade or just an adapter depends. Right, if graph wrapper exposes all the functionality of your graph class, then it's not really a facade, right, because it's not hiding anything. Right, it's just an adapter. Right, but if you had some very complicated graph class, and you only needed to expose like something very simple, not the entire functionality of the graph. That would be called a facade. All right, so here is an example. So I just going to leave it as an exercise so that we can move on. Basically, facade allows us to decrease the number of dependencies. So it reduces the coupling between the client and the subsystem, because everything now goes through our facade, which presents a simplified view. Of course, the purpose of this pattern is to sort of provide a single entry point, a single interface, rather than having the client work directly with this complicated library. All right, here are a few similar patterns, and we will also review them, adapt to proxy, and decorate. All right, coupling, the general idea of coupling is a dependency. All right, so if we say that there is a coupling from A to B, it means that A depends on B. In other words, class A calls methods or uses fields from class B, which of course means that if B changes, we have to revise, we have at least to review code from A because it might be affected. And that's why coupling, as an example of a dependency, is always bad. I mean, if it's unavoidable, so be it, but if we can remove this coupling, we should. So overall, we are trying to have very low coupling, so very few classes that are coupled, because that would reduce the complexity. So here's an example, right? Bad design, classes are strongly coupled, right? Because each edge here in this graph corresponds to coupling. So if we are able to, to revise our design so that the coupling is now like that, so A is coupled to B, B is coupled to C. Now, of course, it's a lot better, right? Because what if A changes? Well, neither B nor C are affected in our better design. What if A changes in our original design? Then you see that both B and C have a dependency on A. So if A changes, B and C have to be changed. And if you look at this graph on the left, you may notice that it's a so-called complete graph, right? So it has the maximum number of edges for a graph with 3 nodes. So it has 6 directed edges, which means everything is coupled to everything else. Right? That's the worst nightmare. So we definitely want to improve this design if at all possible, so that we have fewer dependencies, fewer coupling. Right? So yeah, coupling is bad. Coupling is complexity, and we know why complexity is bad, because complexity is causing cognitive overload. Right? So we want less complexity, and that's why we try to reduce the number of dependencies. Right, so here is, remember we had this design that we started with when we discussed the observer pattern. All right, so we have a client, which is then we discussed has become controller. We have data, which is our model, and we have 2 views. But here views depend directly on the model, or put it differently, data knows about the spreadsheet view and bar chart view. So data actually has a dependency on all the views, right? And that's not good, because what if we need to add another view? We would have to let data, our model, know about this additional view. Right? So that would be not particularly good. We want to kind of make the coupling between the data and the views weaker. What is the weaker form of coupling? It's an interface, right? So instead of directly letting data know about all the types of views, we have this idea of some interface, so that our data knows only about this very general interface, like observer, and then each observer would implement this interface. But introducing this additional interface here relieves the data from the necessity to know about each specific observer. It only needs to know about the observer interface, which let's hope rarely changes. And then if we need to add another view, we just add another class that implements observer. Data doesn't need to know about this new observer, right? Because it doesn't really care what this observer is, as long as it has all the methods that this observer interface prescribes. That's the only thing data cares about, right? If it has an update method to call, that's all data need to know about the views. It doesn't need to know anything else about the specific details of how this view is implemented. Right, so, and if you think about it, Facade promotes exactly this, low coupling. Right, so in another example, on the right, we have, potentially, so we had 3 components of the client and 5 components in the library, so potential number of couplings, interactions is 15, 3 times 5. Whereas here, right, it all goes through our Facade, right, so it's 3 plus 5, the number of dependencies here. So we were able to reduce the coupling. All right, so the idea of separating the model from the view stems from the fact that we want to have the content separate from how this content is visualized, how it appears, right? Because we might need to have multiple ways of representing the same content as text, as voice, as a graph, whereas it's the same content, right? So therefore, the best recommendation is do not connect the appearance and the content. Separate the content, the model, as cleanly as you can from the view. Right? Think about your homework 7. Okay? So you have this pathfinding application that prints basically directions, right? So from this building go west, then from this building go north, and so forth, right? So the strings that make up this the directions, are they going to be appearing in your model where your graph is created, or are they going to be appearing in their view that is responsible for visualizing the state of the model to the user? In the view, exactly. Right? That's why when you're reviewing your class, and if you're looking at your, a class that kind of holds the graph inside, right? So then you shouldn't see any things like, go west or something, right? Because these things will belong to the view, not to the model. Right? And an easy test for that would be, well, if you decide to translate your user interface from English into Spanish, French, then you should only need to update your views, or create another view. So the best approach would be just you have a view which provides English language support. Now you just need to make another view that would do the same thing, but with another language. All right. So if you can do that without touching your model, then it's a good sign, because that means that your model is cleanly separated from the view. Right. So what about the names of buildings like DCC, MRC, VCC, all those names? Do they belong to their view or to their model? Yes, please.
I would think it's probably somewhere in the model. It's not the graph, right?
Yeah. So they belong to the model, right? Because they are part of the data. They're part of the graph. They're part of the RPI campus map, and your graph is representing the campus map, right? And if you imagine translating your entire user interface into Spanish, you're probably not going to be translating building names, right? Building names are gonna, are gonna stay the same. You're only gonna translate the actual words, like, directions, go west, go north, right? Those things, not their names of buildings. All right, so, we want to have as clean separation of their model from the view or multiple views as possible. All right, so let's keep the design exercise. Again, I leave it as an optional exercise. You need to kind of come up with the structure to build a document editor. So let's skip it now and let's look at the other very important pattern that is called composite. Right, so the composite, the idea should be very familiar to you because composite sounds a lot like composition, and it really is it's just the design pattern that captures this idea, right? The has-a relationship, right? So something has a or has multiple other things that comprise this bigger object. So here's an example. We have a glyph. Right, and we have a word which is a glyph. Note that this is a relationship. Right, this is their inheritance. Right, so word is a glyph. Okay, polygon is a glyph. Character is a glyph. Row is a glyph. But at the same time, right, a row consists of glyphs. Okay, so that's why we have this association link where we have one row consists of multiple glyphs, right? So there's a start here. All right, so another example and another design pattern. What if we need multiple ways of formatting the same document, right? So each formatting strategy is different. It's the same document, but formatting strategies are different, right? And we need to somehow account for the fact that there might be many of them. Right? Following the same example with the glyph, right? We can come up with an abstract class. It can also be an interface called formatting strategy right here, right? And then we have specific formatting strategies as concrete classes that inherit from formatting strategy, right? Strategy 1, strategy 2, strategy 3. And note how document consists of formatting strategy. Document has formatting strategies, right? It can actually have more than, in this case, it can only have one, right? So document only has one formatting strategy, all right? So this variation of the same pattern is called a strategy pattern. It is also known as the policy pattern. So basically, we can have multiple algorithms that can be used by a client application, and we want the client to be able to select any of their algorithms, right? So a good example from the standard library of this strategy pattern is their sort method, right? It takes the comparator parameter and then it sorts any collection using that comparator object. Okay, so it doesn't really care what it is sorting, as long as there is a comparator object that can tell for any two elements of the collection whether one of them is greater or they're equal or the other one is greater. That's all that is needed. An example from your homework assignments for the strategy pattern would be, well, imagine, next homework, you are asked to implement this strategy pattern and allow the user to specify the algorithm for finding paths, right? So you've done Dijkstra's algorithm now. It's not the only algorithm, right? It's one of the probably easiest pathfinding algorithms, but there are more advanced and slightly more efficient algorithms, for example, A*, right? So how would you design your code now for homework 7 if you knew that in the future you would add this other algorithm, A*, and allow their user, depending on some criteria, to select whether they want to find the paths using Dijkstra's or A*, Okay, so your code doesn't really care which algorithm, right? There might be 2, 3, 4 different pathfinding or minimum cost finding algorithms, right? So if you envisage that might be the case, then your best bet is to implement their strategy pattern, right? And you can also have, so this is an example with, again, their more recent functional features of Java used to, right? So Lambda functions here are used to implement the strategy pattern, but let's not focus on the functional features of Java for now. All right, so another common task, right? So we keep reviewing our different design patterns, right? So, and again, design pattern is a solution to a common problem, a known solution to a common problem. So a common problem is, making some embellishments to the UI, right? Some decorations, right? So, for example, you have, part of the document and you want to draw a border around it, right? Or have a fancy background for that part of the document. And this idea of attaching some decoration, right, like a border, you can apply not just to the document itself, but to the part of the document or the paragraph or even a single character. So it would be great to have some kind of general approach that would allow you to apply this decoration to different parts that make up the document through their composite pattern. So you see how you can actually combine patterns, right? In order to express the idea that the document consists of sentences, sentences consist of words, words consist of characters, right? So this is an idea that is behind their composite pattern. But now you want to apply their, those embellishments or decorators, and that's why their pattern is called a decorated pattern. Right? So it adds functionality to their underlying classes, preserves the interface, but adds adds some decoration. Like we have a document that consists of multiple glyphs, and then on top of that we have a decorated glyph. Okay? So the document now can use a decorated glyph, which can have multiple decorators, like a border decorator or a scroll decorator. All right, so again, we can grow the number of decorators. For the decorated glyphs, it doesn't really matter. Right? Decorator glyph doesn't need to know all the different types of decorators that can be created, and neither does the document. Okay? So as long as the document, of course, needs to know which glyph which decorated glyph it is dealing with, right? But the glyph can have multiple potential decorators. All right, another scenario, another design pattern. Right, so we often have the idea of a command that our application needs to perform. Right, so for example, there's a common command, quit, right, or exit or close when applied to the application itself. And we know that typically for any application, there might be multiple ways to close it, right? So you might click the X in the top bar of their application. You might quite often have a hotkey like Alt F4, or you can go to the File menu and select Quit or Exit. Okay, so the idea is that there are multiple commands. What if, do we have to write the implementation of each command for each of their ways to invoke this command? That doesn't sound like a good idea. So it would be great if we could have just a general idea of a command that as an action that does something to our application, and have it separate from their ways to invoke this command. Right. That would also allow us to basically keep track of their history of commands, and then if we want to undo certain commands, we would be able to do that. All right. So that also would support undo and redo. All right. So our naive design might look something like that. Right, so we have a widget and we have menu item that says close item, right? So that corresponds to the close command through their menu, like file close. And here's a shortcut button, and it has the close button command. So if we, if we press like, Alt X or Alt F4, whatever the hotkey is for the close, or if there's like a context menu from which we can select this command, right? This is the close button implementation for that. All right, so what's wrong with the design? Well, it's hard to extend, right? Because the same action, closing, is kind of present in more than one object, one for the menu item, one for the shortcut button. All right, so supporting undo, redo would also be hard, right? Because we would have to keep track of not just which command was invoked, but how it was invoked. Was it invoked through the menu item or through the shortcut button? Here is a design pattern that solves this problem. It's called the command pattern. And basically the idea is that it separates their commands from their ways to invoke them, so that we have just general save and close actions, and they are treated as commands, right? And then each command can have multiple ways of invoking it, right? It can be invoked through the menu item, or it can be invoked through something else. For example, also here's a little code snippet, right? So we have this save class just as a class. So a save object would respond to the command of saving the document, and we have it linked to the save menu, save item in the menu, but also to the save button in the shortcut, right? So in our context menu, right? That's the same command invoked through two different methods. All right, and given that, of course, it would be easy to support undo and redo. Right, so for example, the command would now support two methods, execute and unexecute or undo. All right, and then each command that we would only implement it once. What it means to execute cut, what it means to undo cut, and the same for paste. And now, regardless of their method which was used to call a particular command, all right, there's only one command, and it knows how to undo itself, right? So we can just push those objects on a stack to maintain our history, and that would be done. All right, so a command pattern is an example of a group of patterns that is called behavioral patterns. All right, so the request is, right, the command that needs to be invoked is sent to the invoker object, and then that invoker object actually calls the corresponding method of the command object. Okay, so by adding an additional level of indirection, we are getting a more flexible design, a more flexible organization that allows us to support additional functionality. Right, so here is an example of a command demo. Again, let's just briefly discuss it, and then move on to, we have quite a few other patterns to cover. So here, the idea is that we have different file systems, Unix file system and Windows file system. And they are different, but they are all file systems. So we want to sort of hide the differences between file systems by introducing this interface file system receiver. And then our application, right, which is this file system receiver util, is going to support commands. Right? All commands, they stem from the same interface command. So there's open file command, write file, and close file. Right? And command works through a file invoker. Right? So see how a file invoker has this execute method. Right? So that allows us to write our commands so that they're written not against a specific file system like Windows or Unix, or against the file system receiver. So see how the open file command constructor here takes file system receiver. Write file command in the write file command class, write file command, their constructor takes the file system receiver. Right, so that allows us to easily add more file systems if we need to. Right, so if you come up with a third file system receiver, the only change that would be required is to actually implement this class, make it implement the file system receiver interface, and that's all. Implement these three methods: open file, write file, and close file, and that's it. All right. On the other hand, adding a new command would require a little bit more work, right? Because as you can see, the file system receiver and all their and create classes that implement file system receiver would have to override all methods that are, have to implement all methods that are prescribed by this interface, right? So if we are adding another command, I don't know, something file command, it would be added here, right? Something file, something file, something file. All right, so the command pattern is a very common design pattern, right? Because it defines a contract that all commands should now follow, right? In their job of their invoker class, which was this file invoker, is basically to forward the request from the client to the corresponding command object. Right? By having this invoker, our client only depends on the interface of the invoker class and not the actual command object or their interface that represents all their command objects. All right, so that's the basic idea about the command interface. All right, so and yes, you can use it to add spell checking, for example, right? Just as another command. All right, so here is okay. So this slide is out of place. We'll get it, right? It's not in the right place. All right, so the patterns that we covered so far, right? Composite, observer, facade, strategy, command, and now let's. Functional programming, let's not really, let's skip it. And of course, it's not going to be on the exam. I'm not going to be expecting you to write any lambda functions or use streams or any of the more functional features of Java. So let's stop here, and we have more patterns. Right, that's why I'm kind of skipping some of the less important stuff so that we can. Cover more useful design patterns. All right, so we covered a couple of the creational patterns, namely singleton and interning. There's also a variation of the interning pattern that is called flyweight pattern, and the idea of the flyweight is that. Well, if you recall what interning was doing, interning was representing, was limiting the number of objects with a certain state that we can have. Right? So let's say, if we ask for an object, if we are trying to create a new object with the same state that an existing object, then the interning pattern, which just give us that old object that is already created, it would be equal to the object that we are trying to create. Right? So the flyweight pattern takes this idea saying, hey, yes, I can give you an object that has the state that you're asking for. It's an old object. But flyweight allows you, on top of that, to also add some new contents to this object. So it divides the entire object into two parts. One is called the intrinsic state, and the other one is called extrinsic state. So intrinsic is like internal. So the intrinsic state is going to be the same across all objects. So it is intern. Whereas the extrinsic state is going to be different. It's going to be up to the user to to provide this extrinsic state, external, outer state. Right? So objects would differ by only their extrinsic state, not their intrinsic state. All right, so that's the idea, and of course the overall goal of the flyweight pattern. Right, so if we have objects that have parts that differ across objects and then parts that are the same, right? We do that in order to avoid the duplication which we would otherwise have if we had just completely separate objects, right? The intrinsic part in all those objects would be the same, so it would be duplicated. By interning this same part across multiple objects, we are decreasing our memory consumption, and therefore we are also decreasing the number of objects, and that of course leads to better performance. All right, let's look at an example. So here is a circle, all right, and a circle implements the shape interface, and we want to have circles of the 5 colors, right? So the color of the circle is given by this string here, right? By this string here, color, and we want to only ever allow at most 5 different circles with 5 different colors. All right, so that's good, but we have x and y, the coordinates and the radius, and they can be anything. So in this case, right, the intrinsic state would be the color, and the x, y, and the radius would be the extrinsic state. Right, so yes, we don't want to allow more than 5 colors, so at most 5 colors are available, but x, y, and radius can be anything. Right, so this idea is similar to memoization. Right, so remember from your algo class, right? Memoization is an optimization technique that stores the result of an expansive call, in some part of memory. Right, so it basically stores a cached result so that you don't have to recompute it again. So it's the same idea here, right? If we need another red circle, and we already have some red circle, we can just take that red circle and let it have different x, y, and radius. But we save time on that we otherwise would have to spend creating a new red circle, because we are using an old red circle. All right, and here is the outline of the code again. The full code is on the flight weight pattern in the examples on my GitHub. But here is a simplified, abridged version of the code. So see how color is one of the attributes of the circle, and we have a comment saying that it's intrinsic. X, Y, and radius are extrinsic. Right, so when we draw the color, when we draw the circle, we sprint the color x, y, and radius. And here is their shape factory that allows us to produce those circles of the specified color. Okay, so we keep all our interned circles in this circle map, hash map. And whenever the user asks for a circle object, they specify the color. And if we already have that circle of that color in the hash map, we give it to them. If not, we have to create a new circle, because that's the first circle of that color that we encounter. Right? But as soon as we create a circle with a new color, we put it in our circle map. Right? So now hopefully you see what is coming. Whenever someone calls getCircle, they get the same object that was created earlier. Right? So we see a bunch of design patterns here. Right? So first we see there something that is very similar to interning, but it's not interning because we have not just the color, right? But we also have extrinsic state, x, y, and radius. If we didn't have x, y, and radius, that would be the the interning pattern. But we have extrinsic state, that's why it's flyweight, not interning. But we also have the factory object, right? Here, the shape factor class is factory object or abstract factory. So see how quite often different design patterns, they work together. All right, so let's see how this is now going to be used. All right, so this is our driver code. So we are asking our factory for a circle object with some color, right? And we choose color at random. And then once we get this object, we prepare it for our use by setting the extrinsic state, x, y, and radius. See how x, y, and radius are set not inside the color, but set by their external code, by our driver code. All right, and then we use this circle. So if on the next iteration we need by any chance to get the circle of the same color, it's going to be the same object, the same circle object that we have created before. Okay? Then this get circle would extract this old circle object from the cache, give it to us. We would change its x, y, and radius so that we can use it now and use it. Right? And then that object still stays in that hash map that the shape factory maintains. Okay? So this circle map hash map will at most contain 5 different colors. If we assume that we only have these options for the color red, green, blue, white, and black. So it's only going to be one of those 5 values. That's why this circle map will only contain up to 5 objects. Okay? So what is why are we improving on their memory footprint? Well, imagine if you just implemented this problem with a naive approach where you create a new circle with a color x, y, and radius. And next time we need their circle with the same color but different x, y, and radius, you would create a brand new object, right? That would have the same circle, that would have the same color inside of it, right? So if you have 100 red circles, you would have 100 times you would have this red string saved in each of those objects, and you would have 100 of those objects. The flyweight pattern allows us to have just one object, right? So this circle of color red, and then reuse it with different x, y, and radius. Yes, we cannot use 2 objects at the same time, right? So we can only have one red circle that we are dealing with, right? Because there's only one object. But in many cases, this is not really a limitation. All right, so, and this is just the output of this example. So flyweight and interning are very similar, right? So flyweight, if you will, is a more advanced version of interning. Interning would only have the intrinsic state, whereas flyweight has intrinsic state and extrinsic state, right? Flyweight often uses interning, and we saw it right here, right? This is interning. This is very similar code to what we discussed when we talked about the interning design pattern, right? Because we only allow up to so many objects to be created. We store each object with a unique abstract value in cache, in a hash map, and then we reuse that object if it is needed again in the future. All right, here's another idea for the flyweight example. So imagine we have a brush with 3 types of thickness, thick, thin, and medium, and we have brushes of different colors. All right, so now we, in this example, we want the type of the brush to be the intrinsic state and the color to be the extrinsic state that is set by the client. Right? So, for example, if client creates 3 thin pens, all right, so 2 yellow and 1 blue, intrinsic state would be pen And that means that there will be only one pen object of each color type. Alright, so yeah, it looks a lot like interning, but it's a little more complicated, but also more flexible because you can now combine fields, the state that doesn't change, and fields, the extrinsic state that does change. Alright, and here is the class diagram. Alright, yet another example. Bicycle spokes, right? So in a bike race, suppose we have a wheel, right? So spoke has all those parameters: length, diameter, tapered or not, and so forth, and a location. All right. So the location of each spoke is unique, right? It's basically the place on the wheel where that spoke is installed, right? If you follow this example, then if your wheel needs 32 spokes, you would have to have 32 full spoke objects. Right? If you think about those 32 objects, that all of these attributes are probably going to be the same, right? Because of course it's the same diameter because they are spokes in the same wheel, right? They are probably going to be the same material, right? You rarely combine in a single wheel. You rarely use spokes from using different material. Right, so the only real difference would be location. Location would be different for each of those 32 full spoke objects. And of course, that is extremely wasteful, right? Because in the 32 object that you're going to create, all of these attributes are going to be duplicated. They're going to be exactly the same. And only location attribute would be different. So the idea of interning is exactly let's only have this repeated once. Okay, let's call this our extrinsic state, and then location would be our extrinsic state. Okay, so here is the idea. We separate the intrinsic state as a separate class, intrinsic spoke, right? And then we have a subclass of intrinsic spoke that only adds location. Okay, so does that fulfill the goal? Well, not exactly, because this installed spoke full doesn't say space, right? It's the same as full spoke, right? It's just shorter notation, right? But in reality, this installed spoke full will inherit all their fields from the intrinsic spoke. So an installed spoke full object is going to have the same, the same length. Okay. Right. So, but the idea is, let's have only one intrinsic spoke object per wheel, and then have their location. Okay. So that would allow us, if the intrinsic spoke is interned, then it's going to be the same object. And we will have this installed spoke wrapper having this symbol shared across all installed spoke wrapper object, and just location would be different. Okay, so that would be used in space due to implementing the flyweight pattern, right? And it's flyweight because intrinsic spoke is their intrinsic state and location is the extrinsic state. So how do you use these classes then? You would have a class full spoke that says that let's say has a Titan method that needs to be tied to location, right? So Titan is the number of turns that you need to tighten the spoke by, and it's a specific spoke, so at specific location. Right, so how would you perform the align operation on the entire wheel? Right, so you basically go over all the spokes until the wheel is not properly aligned, and you would tighten each of the spokes. Okay, all spokes are in this array full spoke. Okay, so that works perfectly well. All right, so with our intrinsic spoke, you see that we are going to change the type of spokes to intrinsic spoke, right? Because the location is the parameter here, okay? So it is external parameter that is supplied from the collar of Titan, from the wheel, for example. Okay, so now Titan needs to take two parameters, not just the number of turns, but the location as well. But you see how that allowed us to actually use just their intrinsic spoke object here, right? And we know that those objects are going to be all the same. They're going to be interned. All right, so that's the flyweight pattern. As you can see, it is more complicated than interning, but it might be a good way to go, but it might not be. Right, so it is more difficult to debug, and if it's not really bringing you any, giving you any benefits, maybe you better stay away from this pattern. Right, so you have to compute when exactly it is justified to use this flyweight pattern. So if you have thousands of new objects and most of the state of those objects is the same, then yeah, it probably makes sense to use the flyweight pattern. Right? So if object creation is slow or complicated, right? If it's a heavy object, similarly, yes, it might be a good idea to use the flyweight pattern. If objects have some shared state, and that shared state is significant in terms of the number of fields of the memory that those fields occupy, then yes, it's probably justified to use the flyweight pattern. All right, so with the next type of design patterns, right? So we have wrappers, which we kind of saw an example with the graph wrapper, right? So it's a type of an adapter, right, where it just matches their interfaces of the client and the ADT that you created. Right, so yeah, wrapper is not a Ginga 4 pattern, but it is very similar to adapter and to some extent facade. But facade, remember, facade has to be hiding stuff, right? Not just exposing all the functionality. If it exposes all the functionality, it would be the adapter. All right, here are three design patterns that belong to the same group of structural patterns, and that can be easily designated by what they do if we think about the function of the class and the interface. Right, the function meaning the ability, right, the functionality. So adapter, it's not changing the functionality. Functionality is the same, but the interface is different. So think about graph wrapper, right? It's not adding anything that would not be implemented in your graph ADT. It merely matches their interfaces, right? If in your graph ADT, the function is called list nodes, and it returns an iterator of nodes. But your interface, the expectations of the client are that the method is called list children, and it returns an iterator over strings, and their order in which those strings are returned is sorted lexicographically. Then it's just an interface change, right? So you're not adding any functionality to the graph. You're just matching the expectations of the client. So that's adapter. All right, what if the functionality is altered, but the interface is the same? It's called a decorator, okay? We have seen an example of this design pattern already. So with the decorator, functionality has to be different, right? So we have to decorate it, right? Excuse me, we have to add something, right? We have to add borders or underlining or like bold to our to our glyphs, right? So we have to add functionality for this to be a decorator. And interface, it can be the same or it can be changed. It really depends. All right, and then proxy is a design pattern which does not change the functionality, does not change the interface. So the question arises, so what does it change, right, if it's not changing functionality or the interface? And it turns out that, well, there are other properties of a class other than functionality and interface. Right? For example, access level, or security, or the origin of the object, and proxy might change that without really changing functionality and interface. So an example would be their proxy might control access to their underlying library and preventing access if no proper credentials are presented. If proper credentials are presented, then proxy exposes full functionality and the same interface as the underlying class. So proxy is like a wrapper, right? Not just a transparent wrapper, but a wrapper with access control, right? So that would be an example of a wrapper. All right, so adapter pattern, really not too much to talk about, right? Because we have seen, graph wrapper is essentially an adapter. So change the interface without changing the functionality. That would allow the client to enjoy the functionality without, changing the interface that the client expects. Right? So the client may call list children, and their graph wrapper would translate their call to list children to their call of list nodes of the underlying graph library. Right? So the reasons are obvious. We want to match the interfaces of the client and their library. So yeah, we cannot rename methods per se, right? But we can make an impression that we are renaming methods, right? So we don't have to rename list nodes in your graph, but we want to sort of make an impression that we renamed it to list children, which is what the client expects. Convert units, right? That's another known common use for the adapter pattern. Imagine that your campus path needs to return the total distance traveled, and it turns it in pixel units. Okay, but then what if the client expects the distance to be in actual feet, yards, miles, units? Okay, so do you necessarily have to change your campus paths? No, not necessarily, because you might build this conversion into an adapter class. Okay? So that an adapter would call their corresponding method of the campus paths, get their length of the path in pixel units, and then translate it into miles or feet or whatever. Okay? So that is another very, very common use of adapters. Another, reformat the output. Right? Imagine that your campus path produces the directions not in the format that the client wants. Maybe they want it to be in HTML instead of plain text. Right? So an adapter pattern could take that plain text output of the directions from one building to another and convert it into HTML, right? Add the HTML tags to reformat the output. Again, why it is adapter? Because it's not considered adding new functionality, right? So it is just getting a new different interface, right? So if reformatting the output, if it's extensive, it may actually fall under the decorator. Right? If it's extensive, yes, you may argue that it has already become a decorator because we are decorating the text with additional markup, which makes it HTML. All right, so yeah, basically the adapter is the bridge between two interfaces, one of the client, one of the library. If they are not compatible, the adapter can match that difference. Quite often, it may happen when your client was working with some library directly, and then that library got phased out. Okay, so the library was discontinued, and now you're like, oh, okay, I can purchase another library, but that new library, it has a very different interface. And of course, you don't want to change your client because you know that it works, right? You don't want to really touch that code. So what you do is you purchase this new library, and then you write your adapter that translates the calls that their interface was, that the client was doing originally to the old library, to the calls to the new library. So basically, you are hiding from your client. You are hiding the fact that the library has changed, right? And that allows you to not change their client at all. All right, so yeah, here's another example adapter demo, but let's move on and look at their more adapter pattern. All right, so here we have a shape, all right, and different types of shapes like line and text. And then we have text view. So the motivation here is to reuse a class with an interface that is different than the interface of our class. Right. So, so that would be another example of an adapter pattern. All right. What else? Yeah, Django 4, it describes two types of adapters, class adapters and object adapters. Right, so they are different in that class adapters, they use multiple inheritance to adapt one interface to another. Right, and this multiple inheritance immediately tells you, well, that's not something we can do in Java. Right, so we need to use interfaces. The original Django 4 examples are in C++, not in Java. And then we can have object adapters, right, that depend on object compositions. All right, so let's look at some examples. All right, so here is interface rectangle, and we have two classes, the client class and the non-scalable rectangle class. Okay, so the client has client method that takes a rectangle, and then it calls scale on that rectangle. So all rectangles would have this scale method. But if there is a non-scalable rectangle, it doesn't have the scale method. And as you can see, it's not a rectangle. It doesn't implement the rectangle interface. Right? So can we use non-scalable rectangle in client instead? No, right? Because non-scalable rectangle is not a rectangle according to this. So what we could do is use a class adapter that adapts via subclassing. So we can make a scalable rectangle that extends non-scalable rectangle and implements rectangle. So see how we are kind of closing the gap between the expectations of the client, they get rectangle, and the fact that the rectangle that we want to give them is non-scalable rectangle because it doesn't have the scale method, and so it's not a rectangle in the sense of this interface. All right, so here we are kind of closing this gap, and we are saying, well, we're going to have the implementation of the scale method here because, of course, interface rectangle calls for the scale method, and here we can use get width, set height, get height of the underlying non-scalable rectangle. So it's in red because it is coming from this red non-scalable rectangle. Scale is blue because it is our responsibility for the rectangle interface to implement this scale method. All right, so that would be an example of a class adapter. Object adapter adapts via delegation. So basically, it forwards the work to the delegate. So an example of an object adapter would be we have non-scalable rectangle here through composition as the delegate, right? And then when we need to compute the scale and call set width and get width, we would use the corresponding method by calling them from the arc object. So comparing the class adapter and object adapter, we clearly see the difference. Here we make scalable rectangle a subclass of non-scalable rectangle. Here we include non-scalable rectangle into the scalable rectangle through composition. So here are two different approaches, subclassing and composition, delegation. Right, so subclassing obviously has the convenience that it automatically gives us access to all methods in the superclass, so it can be more efficient. Delegation is in some sense more flexible because it permits removal of methods. Well, not the literal removal, but no one forces you to expose the methods that you do not want. Right, so here, scalable rectangle 1 would have all methods of non-scalable rectangle plus the scale method. Right? What if you want to get rid of some of the non-scalable rectangle methods? You cannot. Here, you only expose methods that you want to expose. So if there is a method in non-scalable rectangle that you don't want to expose, well, here you see that we're not exposing it, okay? Because there is no method that someone could call that would translate to r dot whatever you didn't want to expose. Okay, so that is in that sense a little bit more flexible. All right. So in many cases, real world parameters, you can quite often have a hard time telling whether it's an adapter, decorator, or proxy, or a little bit of everything. So differences may be subtle, but please beware that if we ask you to identify a design pattern that a particular piece of code implements on the final exam, then we will try to make sure that these examples, they are pretty obvious, right? So, just saying, well, it's one of their structural patterns is not going to be an accepted answer. Or saying, well, it's it's adapter, decorator, and proxy, all of them, right? So, no, you actually have to look into what this code does before you are able to say that it does them all. And because we will try, of course, not to give you examples where it would be like, a big mix of anything. Okay, so, all right, so this is just another example of an adapter, object adapter. So I think we've seen enough examples, so we can skip this one. All right, and a couple exercises that I think we can. It's related to the previous, so we can skip it. All right, it's the continuation of that service factor example that we decided to skip. All right, so next important pattern is called composite. Right, we have already seen it, right? But now we will look at it deeper because composite is a very important concept. Right, it expresses their part-whole relationships, this has-and relationship, and therefore it is very, very common. So for example, think about an expression 5 plus 2 times 7, right? And let's say 5 plus 2 is in parentheses. Okay, so how can we treat this expression if we had to model it and let's say evaluate in our code? We would model it through the composite pattern, right? Because yes, we have values like constants, 5, 7, and we have operations. But the result of an operation is an expression. An expression can participate in other expressions, right? So it's sort of kind of recursive, but it also has this composition idea. So expression consists of sub-expressions, and each sub-expression is an expression, so it consists of other sub-expressions. All right, so let's look at some of the examples. Here is a composite that demonstrates their organizational structure of some organizations. So we see that an employee can be a developer or a manager. Right, so employee is our superclass, developer and manager are subclasses, but there is this association relationship as well, which is saying that a manager can manage employees, right? Multiple employees, right? Manager themselves is an employee, but manager also has employees that they manage. Okay? So developer is a much simpler class. It doesn't have anyone. So developer is just an employee. And so we can have that kind of class hierarchy allows us to build charts where we have a manager who manages other employees. Those employees may be just developers, or they may be managers who in turn manage others, right? Developers, and maybe there's another manager here. So if that is a manager, they would have more developers that they manage. All right, so here is how it could have been implemented. So this is composite demo. Again, example is the full example is on the GitHub. All right, so we have this employee with some operations that would be supported by all employees, no matter manager or developer. We have manager that implements an employee. So manager has name and salary, and it contains a list of employees that this manager manages. So we have add and remove methods to add or remove employees from this employees list. Yeah, we can also look at older employees that are managed by this manager. GetChild returns us the ith child, the ith element from that employees list. All right, so now developer is also an employee. Developer implements an employee. The developers have name and salary, but they do not have anyone to manage. All right, so this method is not applicable to this class, right? Therefore, it shouldn't be really there. Note how employee, in this case, interface requires us to have this method added. Okay, so that's not a good idea actually, right? Because we know that a developer would not have any meaningful implementation for this add method, right? We kind of want to remove that method, not to implement it. All right, same with GetChild. Okay, so right. So in this composite example, right, we see that the object, like a manager object, has a list of other objects, employee objects, or contains other employee objects. Right, so that's the idea. And we can have more examples. So here's an example where we have a letter that consists of words. Words consist of letters. Letter consists of sentences. Sentences consist of words. Words consist of letters. Okay. At the same time, word, letter, and sentence, they are all letter composites. Right? So there is an inheritance here in addition to composition. Right? So following our bicycle set of examples, right? So a bicycle has wheels, wheels have skewers, and wheels have hubs, and spokes, right? So again, another example of composition. All right, so how would we code this bicycle example? Well, we can have an abstract class bicycle component, and then have all the parts of the bicycle subclass from bicycle component. Okay, so each class, skewer, wheel, and so forth, they would have a cost, and that they might be not the leaf nodes in our component hierarchy, right? But they might in turn consist of other things. For example, skewer does not consist of anything, right? So it's a leaf node. All right, it just has the price, and the cost is just the price returned. Whereas wheel is a composite itself. Wheel consists of the skewer, hub, and other stuff. And that's why the cost is computed as the cost of all components. So we see skewer cost, hub cost, and so forth, plus the assembly cost. Right? So we can actually make this implementation a little better by using the bicycle component for their declared type of skewer and hub instead of making them fields of type skewer and hub. Why? Well, because then instead of calling skewer.cost and hub.cost, we would be able to basically have a list instead of having them as separate fields. We could have a list of components. All of them would have type bicycle component. And we know that bicycle component has the cost, so here we could have just a for each loop over all components that make up the wheel and call cost on all of them, right? Because imagine you have 25 different components in a wheel, right? You'd get tired listing them all here and then calling dot cost on each of those 25 variables, right? Fields, not variables, right? So you, no, fields, yeah, that fields. So you want to have a way of easily representing a big number of components, right? So another example, Boolean expressions, right? So that's something that would probably be closest to you in understanding of why composites are useful, right? So we have the Boolean expression, which can be a variable or a constant, like true and false. Or it can be an expression, like x or true, x and true. So we have or expressions, and not expressions. So they, in turn, are composites themselves, right? And or and not are collections of expressions. Whereas variable and constants are leaves. They are atomic units. They do not consist of anything else, right? They're sort of terminal. All right, so if we build the hierarchy of our Boolean expressions, then of course the next natural question would be, well, how do we for example, evaluate our expression? How do we go over an expression? All right, how do we examine all the components that make up our big expression? And here are several types of approaches are possible, but the overall task that we're trying to accomplish here is once the composite has been built, how do we traverse the composites? Right. So here's an example of representing Boolean expressions with a composite. Right. So we have abstract class Boolean expression. So everything in our model is a Boolean expression. A variable is a Boolean expression. A constant is a Boolean expression. And expression is a Boolean expression, and so forth. So our atomic units, constant and variables, they are terminal. They do not consist of any other Boolean expressions. Right? So what can we do with a constant? Well, we want to keep the value of the constant, hence this field const, and then we should be able to evaluate the constant, right? Because one thing that we definitely want to do with our Boolean expression is to evaluate it. Right? So eval is called by the Boolean expression, their superclass. Therefore, constant has to provide an implementation of eval. And in this case, it's very straightforward. We return the constant that this object represents. Variable name is a little bit more complicated because we have the variable name and the variable value. So var name is the variable name, like ABC, and the value is actually stored in some other object that is called context, right? Which is essentially a key value storage, a key value dictionary. So if we know the name of the variable, we can call our context and say, please look up the value for variable name this. And it will give us the value. The value, of course, is going to be a Boolean, right? Because all variables are Boolean, so we can directly return that value. Eval returns a Boolean. All right, so those are two atomic expressions. What about more complicated expressions like and, or, and not? Well, they are not atomic, which means they consist of sub-expressions. And or will have two sub-expressions because they are binary, and not expression is only going to have one sub-expression because it is unary. So and expression has two sub-expressions, left and right. Evaluating their and expression means that we have to evaluate their left expression first, and then right expression, and then combine the two results with the Boolean and. Right, so and or and not will have very similar implementations, so we skip them, but there's Boolean demo project in GitHub that on GitHub that you can run. Okay, so here is what our class diagram looks like. All right, we have 5 types of expressions. Bool expression is our superclass, and the constant and varx, they do not have any parts that they include, but not, or, and have sub-expressions, and not expression has one sub-expression because it's unary, or and have two sub-expressions, right? Because they are binary, so we have 2 here for the cardinality. All right, so those are composite objects, those are non-composite atomic. So if we represent the object structure with like an organizational chart, right, or a tree, right? So here is the piece of code that creates the objects, and here is the tree that corresponds to this hierarchy of objects. Right? And here is the expression that we are trying to represent: x or true in parentheses and y. So that means that at the very top of our tree, what is going to be the expression? Well, it's going to be the expression that will be, it's going to be the operation that will be evaluated last, right? So as the last step, we would take whatever that result is and y, right? That's why I'm here for the and expression for the tree node, saying x or true and y, right? And then the right sub-expression is just the variable expression y, it's right here. The left expression is an or expression, x or true, which in turn, this or expression has the left sub-expression and right sub-expression, x and true. So that tree gives us a very good view of the order in which operations are going to be performed. Right? First, we will evaluate x, then true, then this or x, then y, and only at the last step, this and expression. Okay? So in the code, we kind of see the opposite. First, listed is the expression that will be evaluated last, and the outermost expression, and expression. All right, yeah, and here is a little exercise for you to draw write the code and draw the tree that represents this expression. All right, that would be it. Right? So yeah, and thinking about it, that probably makes a good quiz question, right? So given an expression, write the code and write the tree that represents this expression. All right, so that would be the general structure of the composite, right? So we have some components that all subclass from their abstract component class, and then some components are leaves, right? They're atomics, so they do not have anything else, but other components are composites, so they have children like that. All right, so their structure, their composite would be the component itself, and 2 types of specific components, atomics or leaves, and composites. And then, of course, we have the client. That would be the driver code that creates the entire object structure. All right, Now, what if we want to add flexibility to how our hierarchy that we constructed with the composite pattern there are changes that we can survive, that we can support, right? So we can add remove methods so that we can add new components or remove components, existing components, and list children, right? So list for any given component, we can ask it to give us their consistent parts. Okay? If it's a composite, right? So if it's a leaf, then no, we're not going to have an implementation for get child. Right? But if it's a composite, it has to support get child. All right, so.
Wait, why do the leaves not have to support get child?
Because the leaves do not have children. If you look at the leaves in this tree, they are all Varax, constant Varax. They cannot be an or expression or and expression or not expression. Right? Because here, right, composites have this association link with another component. Composites have other components. Leaves do not have this link back to the component. So a leaf node, a leaf object does not include other components. Does that make sense? All right, and decorators. All right, so yeah, we've already talked about decorators, right? So it's like a wrapper, but with added functionality. Right, so here's another example of sandwich. Right, so we can have a baseline sandwich, but we can add decorations to it. Like cheese or salami or whatever you like on your sandwich. Right, so there is a sandwich demo example. Again, we just going to discuss it briefly. Right, so we can have a sandwich class with basic sandwich bread and filling. Right, but you might want to add decorators, right, like all the different types of toppings. All right, so that's the idea of a decorator. Let's see how it would be implemented in Java code. So we have a generic sandwich. All right, it's not a generic class, right? Don't be fooled by the name. It just says like baseline sandwich, so to speak. Then it implements the sandwich abstract class, right? See, it's in italics, so it's abstract. And then we have a sandwich decorator class that is a sandwich, right? And that is a base class for all the decorators, like cheese decorator or lettuce decorator. Okay? So each of the decorators adds their corresponding topping, and of course it adds the price. Okay? Because the more toppings, the more expensive our sandwich becomes, right? So decorations are not necessarily free. Right, so we see how this link here corresponds to the association, right? So which means that our sandwich has decorations, right? And cheese decorator is just one of the examples.
So,
all right. Yeah.
Sorry. So the sandwich decorator class is what is actively changing the sandwich to have these fillings, right? For cheese and whatnot. So that is this isn't really a question, this is an understanding check.
No, sandwich does not necessarily know about specific decorators. Decorators are applied on top of the sandwich. All right, let's look at the full code. I think it's, if the question arose, it's probably an indication that we need to look at the actual code so that it makes sense. so our abstract class sandwich, right? It has the description, get description, and abstract price, no implementation. Generic sandwich, our baseline sandwich, right? Constructor sets a descriptor, price is free, whatever, $3. All right, so now we have sandwich decorator, right, which extends sandwich and has an abstract price. Okay, so it's an abstract class, right? So it's just the base for all their decorators. So now the decorators, right? So here's a cheese decorator. Cheese decorator contains the sandwich which it decorates, right? Not the other way around. So when we apply the decorator, we need to know which sandwich to apply it to, right? So sandwich is passed as a parameter to the constructor of the decorator, right? And then the decorator, of course, would know what it applies, cheese, and it would know how much it is going to add to the cost of their sandwich price, 50 cents for the cheese. Okay, and you can, of course, have multiple decorators that would vary in what they add to the description and what they add to the price. So when we have this driver code, we first create our generic sandwich, right? And we can check right away what the price of that sandwich is, and then we add the decorator to the sandwich. Right? The sandwich object itself doesn't know anything about the decorators. Right? It's the other way around. It's their sandwich that is contained in the decorator. Right? But this decorated sandwich is still a sandwich. Right? So see how we create a new cheese decorator, give it my sandwich, and then assign the new object to my sandwich as well. Okay? So, and this is the point of making a cheese decorator implement sandwich decorator, because sandwich decorator extends sandwich. So cheese decorator is a sandwich through sandwich decorator. Okay? So that allows us to use their same variable of type sandwich to hold both their baseline generic sandwich and any of the decorated sandwiches. Right, so when we run this, right, we should be able to see that first we started with a generic sandwich, $3, and then once we added the decorator, so our sandwich increased in price, so now it's $3.50. All right. So now here's a question for you. Can I go with double cheese? No?
Does it guess it depends on the .add function, right?
Well, what I'm thinking, like, can I use their decorated sandwich as a sandwich?
Yeah, because
And apply the decorator to the already decorated sandwich?
you should be able to, because it's a sandwich.
And sure thing, it works. Right? So yeah, nothing prevents you from adding a decorator to a decorator. You can chain them. Yeah. All right. All right, so those were decorators. All right, the structure of the decorator, right, more examples. Right, so we can have a decorator with their components of the text. Right, so like this idea of adding borders and underlining whatever decoration to our text. Right, so here's our border decorator that extends the decorator. Here's our scroll decorator that extends the decorator. Right, and here is, so this example is very similar to the sandwich demo, right? So we have a client that creates just a text view, and then it creates a decorated text view by applying backseat to their original plane component. Right, and this is just another version, delegation, not that much similar. All right, the idea of decorating is widely used in Java I/O package and in many others. Right, so if you have an input string, it's a byte strings, but you can treat it as a file, as a decorated file input stream, or filtered input stream. Right, so you can create or a buffered input stream. So you can create a buffered input stream, pass an underlying stream to it. Right, so you would be like new buffered input stream and then new some other type of stream. Right, so this is very common. Right, like that. Readers with character input streams, they are very common in Java I/O. All right, another decorator example where we, all right, 515. All right, let's stop here and we will restart with this uppercase converter example. I will go over the code for that one.